All right, geometry students, thank you for taking the time to get your notes taken care of. I'm assuming you're getting a little bit better at this whole Cornell note format. This will probably be the last time that I really kind of deliberately help you through the Cornell format. So if you're still struggling with it past this lesson, probably drop by the room at some point in time so we can explain it. But here we go. Today we are looking at how points, lines, and planes interact. Okay, so copy down your title and your objective and your essential question. Okay, so we're going to start off with our objective. Our objective for today is to acquire an understanding of how Euclid's structures interact in diagrams. Okay, so you need to copy down your objective. The student will acquire an understanding of how Euclid structures interact in diagrams. And of course, Euclid's main three structures are points and lines and planes. Now, the language objective you do not have to copy down. It is my information to you. What we're going to do is we are going to apply properties of points, lines, and planes in order to identify these interacting situations in diagrams and in real life. We're going to be looking at some of our surroundings and seeing if we can spot some of these objects. The essential question, which you do need to copy down, is can you identify the new properties when you see them? So that'll be the question that you ask yourself by the time you get to the end of the assignment in class. Can I identify the new properties when I see them? Okay. As always, anytime you need more time to copy something down, press pause on the video and then hit play when you are ready to move on. Okay, so here we go. All right, now here is a definition that y'all have had for a long time. However, the definition that you've had from junior high is unfortunately a little bit inadequate. Okay, lines that exist in the same plane but do not intersect are called parallel lines. Okay, so the term parallel lines goes out on the left side in your Cornell notes, and the definition comes over on the right. And the definition is lines that exist in the same plane but do not intersect are called parallel lines. Back in junior high, you probably got a definition for parallel lines being just lines that don't touch. Okay, well, unfortunately, there's a lot of lines in geometry that do not touch. That does not make them parallel. So the old definition that we learned back in junior high, we're going to have to adjust that one. And you're going to find that's going to be the case in a lot of instances as we move through geometry. Okay, there are several ways that we can tell that lines are parallel or not. And as I've already said, it is not good enough to simply say they don't touch. That means they're parallel, because that is absolutely not true. Okay, one of the ways that we're going to be looking at a lot this year is the lines themselves may contain small arrows or triangles in the body of the lines. I'll show you what that looks like here in just a moment. The lines may contain small arrows or triangles in the body of the lines. Okay, so we're going to look at a couple of different sets here, a couple different examples. Okay, so one of the ways we're looking at is the statement number one referred to small arrows. That's an example of what small arrows in the body of the lines might look like. When you see that, that is a communication to us that the two lines that possess those marks are parallel to each other. Okay, the triangles that is referred to may look something similar to that one. Okay, so when you see matching triangles in the lines, in the body of the lines like that, that means that they are going to be parallel. Now, do not get these, either of these two sets of markers confused with the arrows that show up at the end of the lines, indicating that the lines go on infinitely in each direction. These guys will show up out in the body of the lines. Okay, the second way that we can tell if lines are parallel or not is to look for external information that's going on with the diagram. One of the things that you're going to find as we go deeper and deeper into geometry is that some of the diagrams can get really very complicated, and there can be a lot of clutter going on inside of the diagrams. Okay, so when that happens, a lot of times instead of marking information in the picture to show us that something is going on, they will actually state the information off to the side of the diagram, similar to what I've done there. Obviously, in the diagram, you have line AB, you have line CD, and then over to the side, they have some shorthand notation. It says line AB, and then you have the double slashes there, and then it says line CD. The double slash is an abbreviation for is parallel to. Line AB is parallel to line CD, is what was just said with that notation. Okay. Now, the third and final major way that we're going to be watching out for lines being parallel has to deal with the math. There's going to be plenty of equations and things like that that we are going to be working with going on surrounding our parallel lines. And if the math agrees with something that's happening in the picture, then that will tell us that the lines are parallel or are not parallel, and that will actually be a very large discussion that we're going to have down the road. Okay, but for now, just understand that there's mathematical information going on, and if the math says so, then yes, they are parallel. Okay, now a little side note here. Okay, and I'm not real sure how you're going to do this in your notes, but do the best that you can. We're going to start off with a couple of lines. And I want to prove a little bit of a point here. Now, we have two lines that for all intents and purposes do appear to be parallel. Okay, looks by the naked eye that if you were to extend these lines in each direction, that they are most likely going to run side by side forever, and they are not going to intersect. And again, this is a very small space, but you're going to be facing a lot of small spaces as you do your work on your worksheets and taking tests on regular pieces of paper. These diagrams are not going to be very big. Okay. However, if you extend those lines further, okay, now look at the exact same lines again. Okay, I think it's really pretty clear to see that right now, if you at the top right edge of the lines, they are closer together than they are down at the bottom left. Okay, and it's very clear to see that with the lines extended. So just keep in mind, okay, in small spaces, you absolutely cannot tell what is going on. You cannot see parallel in a diagram. Okay, so looks can be deceiving. So basically, we are just making the statement establishing we are never going to decide that lines are parallel simply because they look like it. That is not going to be good enough. We're going to need one of the three pieces of information that we just said, how we're going to tell if lines are parallel or not. Okay. Next, new definition. Okay, unless you had a very, very good geometry or junior high teacher, you probably have not heard this term before, and the term is skew lines. Okay, so skew is going to go over on the left side of your paper, and the definition that accompanies it goes over on the right side. And the definition is two lines that are do not exist in the same plane and do not intersect. Now, this is the reason why we had to get rid of the old junior high definition for parallel, because they said parallel simply means they don't touch. Well, skew lines do not touch either. The difference is parallel lines are in the same plane, skew lines are not in the same plane. So let's look at a diagram, see if we can understand what's going on with skew lines. Now, one of the things that you're going to have to kind of come to accept in geometry is that much of our discussion in geometry deals with the three-dimensional world, the real world. However, we are putting our notes onto two-dimensional paper. That makes some of the diagrams a little bit difficult for us to draw. You're just going to have to do the best that you can so that later on when you're studying, hopefully you'll be able to tell what it was you were trying to communicate. So it's difficult to draw skew lines in two dimensions. Consider a plane with a couple of lines going on around it. Okay, here's how we draw a plane, very much like a parallelogram, even though we know, as we said, planes do not really have this boundary running around it. We just draw it so we can see it. Okay, now a couple of lines are going to interact with our plane. Okay, so here comes a line, and this is a typical depiction of a line that is passing through a plane. So we have line AB, and you can see that as it enters the plane, there is another point, another black dot showing up right in there. Okay, and as the line passes into this plane, goes through that dot, then the line becomes dotted or dashed. Okay, that is a communication to us that we understand the line is there, but something is blocking our view. And in this case, it is the plane. The plane passing in front of the line right through this area is basically blocking our view, so we cannot actually see the line, but we do know it's back there. And after the line emerges from the edge of the plane, then we can see it again. So that is how they're going to communicate when a line passes into and through a plane and is behind it and then comes out of the other side. Okay, so there we have line AB passing through the plane, and I'm color coding it as best I can so that you can keep everything straight on these complicated definitions. Okay, and then we're going to have another line. This one is actually in the plane, and we can tell that this one is in the plane because, number one, we do not have any type of a point along the body of line CD that would indicate that it is intersecting the plane like we had with line say or the line AB right there. Okay. Also, we can fully view all of line CD. It does not have that dashed or dotted area to indicate that it has passed out of our sight and is hiding behind the plane. So we have another line that is in the plane, and it's line CD. So line AB passes through the plane, while line CD is in the plane. Let's look back at the definition for skew and see if this fits it. They do not exist in the same plane, and they do not hit each other. Now, how do you know that they don't hit each other? It looks like they cross right here in this area. But remember, the dashed part of line AB is showing that it has passed into the plane, through the plane, and is on the bottom side of that plane now, where line CD is entirely in the plane. So even though our vision kind of mashes these two lines together and makes it look like they're intersecting right there, they're not actually touching. They are just passing one in front of the other. In fact, if the person who came up with this diagram, which was me, wanted you to think that these two did intersect, we would put a point right there where the crosshairs of my mouse are at. So there would actually be a point right there indicating to us that those two lines did in fact hit and join together for that moment. So these are absolutely skew lines. They do not intersect. They are not parallel. They are skew. Okay? Now, let's look at some of these things when they start running into each other. If two lines, rays, or line segment intersect, they intersect to form a single point. And if you think about it, that makes absolute sense. It's not like the two lines are going to bend back around and hit each other again. Here we have line AB. Okay, then along comes ray CD and makes contact with line AB. Okay, so line AB and ray CD, they intersect, and the intersection is a single location, which is a point. So line AB and ray CD intersect to form point E. Now keep in mind on your ray, remember you must absolutely enter or list the end point first. C was the end point. That's why I listed it first. D is the side that went on forever, so it got listed last. Okay, rays are specific about the way you have to name them. Okay, now this time instead of two lines, two first-dimensional objects running into each other, let's look at what happens when a plane, which is a second-dimensional object, runs into a line ray or line segment, which is a first-dimensional object. Once again, the intersection that is formed is merely a point. Okay, so let's take a look at it. There goes line segment FG. Okay, and let's say line segment FG passes through a plane, which is plane H in this case. As you can see, once the line segment has made contact with it, the line segment's not coming back. The plane's not going to bend around and hit the line segment again. You only get that one intersection, and that one intersection is a point, in this case, point I. Okay, oh, now this page, I forgot to break it into little pieces, but let's take a look at it anyway. Okay, this time is the situation where we have two planes intersecting each other. Now this one's the oddball. Two-dimensional planes running into each other. The intersection between the two planes is actually a line. Now you may need to hit the pause button if you need some time to try to scribble this guy down. It's a more complicated drawing than the other two. Okay, but there you have it. We have two planes, plane R and plane S, and they are intersecting at line T. And you can see I've added in the dashed lines where plane R is out of our sight. We cannot see it, so that edge is kind of hiding behind plane S. And then similarly, this dotted line on plane S where we cannot see it because it's hiding behind plane R. Now remember on this, the planes do not actually have these boundaries. We've drawn them in so that we can see the plane. But if the boundaries aren't actually there, then that would mean that T, even though it looks like a line segment, it is actually a line. As plane S and plane R come further forward and further forward and further forward, line T will also come further forward with it. And same thing going backward, as plane S and plane R both continue on backwards, line T is going to have to extend out backwards with it. So while that T guy in there looks like a line segment, remember that he is actually a line because those planes do continue on forward and backward infinitely. Okay, so that is the information. At this point in time, you need to summarize your information in your notes for yourself, jot down any questions that you may need to come in and ask, and keep the essential question in the back of your mind. Can I identify the new properties when I see them? Okay, that is all. I appreciate you finding time to get your notes taken care of, and I'll see you in class.